On the left there, that's our little healthcare system. What looks like a garden hose represents what we actually like to call the fire hose of healthcare data coming from that health system. That little garden hose makes it slightly less intimidating, but trust us, it is as intimidating as a fire hose at times. Thanks for joining me today, everybody. Let's jump right in. I'll start with a quick intro. I actually consider myself to be a bit of a healthcare tech newbie. I've been with Redox for less than 2 years, and that's actually the extent of my healthcare technology experience. Before that, I spent about 11 years cutting my teeth doing software engineering on data-intensive systems in investment banking trading with two of the bigger investment banks in the world. So that's where I got my start. That's where I learned how to build and operate data-intensive software. And I've brought some of that to healthcare and hopefully can help solve some of those problems in a way that helps our customers resolve some of that friction that everybody feels in healthcare technology. So what we're going to talk about today. I skipped. I'm the engineering team lead here at Redox for an area called Data on Demand in our engineering team. You may have seen some marketing material recently. It's a new product offering that we've launched. I'm going to start by explaining what that is and what Data on Demand is for on the Redox platform. Then we're going to jump into what I see as some basic barriers to entry for getting into healthcare integration. So essentially things that everybody has to go through in order to start integrating with health systems and to sell their products to health systems. And we'll talk about kind of a minimum viable architecture for starting that integration and starting to ingest and store healthcare data. And we'll talk about a lot of the complexity behind that. After that, we'll jump into what it takes to scale those solutions. So I'm sure it's everyone's dream who's developing healthcare software to scale their product to tens, hundreds, thousands of health systems. And we're going to talk about some of the friction around the scaling the integration to that level. And then I'm hoping to do a live demo of our Data on Demand offering and how essentially the outcomes of some of the problems we've solved in this space. And then we'll just round up with a summary of what I talked about and take questions at the end. So jumping right in, Data on Demand. Basic idea is to make healthcare system data available for query in a consistent and normalized way, regardless of the healthcare system's EHR or API. Basically turning healthcare data push feeds into point-in-time query APIs. There's this constant discussion in any industry of what's better, real-time events or query. My opinion is both, and sometimes neither. There's kind of no one-size-fits-all. Every architecture calls for a different way to receive data, whether that's point in time with a query request or whether that's receiving real-time events. It's really based on the product itself and the architecture. So at Redox, we had done pretty well solving the real-time events and normalizing integration workflows for real-time events, but a lot of our customers had found that there was a big need for normalizing query and get requests across healthcare systems. And so that's really what Data on Demand was meant to solve. One thing interesting about Data on Demand is the way we built it is we integrated on the Redox platform like any of our customers would. So we created destinations and start ingesting Redox API across our platform, just like any of our customers would do. So I bring that up because it gives us a really unique perspective about the friction that our customers go through, not just integrating over our platform, but integrating with any healthcare data push feed. So it's given us a lot of ability to empathize with a lot of the friction that is inherent in these types of integrations. So minimum viable architecture. When you get into healthcare integration, there's kind of a minimum amount of work that you have to do to start receiving data and integrating that healthcare data into your system and making it valuable and useful to your product. On the left there, that's our little healthcare system. And what looks like a garden hose represents what we actually like to call the fire hose of healthcare data coming from that health system. That little garden hose makes it slightly less intimidating, but trust us, it is as intimidating as a fire hose at times. So to start ingesting and consuming that fire hose, you basically have to have some sort of way to ingest the data, transform the data into your schema, and persist that data alongside your product's data. And then probably some sort of data access or read layer that combines your own product's data, your own software system's data, with the data of the healthcare system, and serves it up in a nice way for your product. So this is obviously very high level, and there's a number of things that you could do within this, but it's just an example of the minimum things that you need to think about in your architecture when initially integrating with a health system and consuming a healthcare data feed. So that seemed easy enough. So what are some of the kind of initial barriers to entry that everybody has to solve? Let's go through a few of them. I'm not going to hit on all of them. There are a lot, but I'm going to hit on some of the common ones that everybody seems to encounter and have trouble with. So patient identification, this is probably one of the biggest points of friction in all of healthcare integration. When it comes to integrating with a healthcare system, there's some things you have to know about patient identification. One, there's potentially multiple identifiers for any single patient in a healthcare system, or on occasion. There are sometimes no identifiers assigned to a patient. Another big complexity is patient record duplication. Almost all healthcare systems have patient record duplications. I've seen statistics that say anywhere from 5 to 10% of patients in a health system are potentially duplicates. So what are some of the solutions to this, and how do you approach this problem upon initially integrating with a health system? One is have a conversation early on with the health system to understand what identifiers they are sending with their patient events that can be considered unique and can be considered reliable. So what we did with data on demand is we call these primary identifiers, and we configure for a health system after identifying what identifiers are going to be unique and reliable. We configure those as primary identifiers. We still will ingest secondary identifiers, persist those with the patients, and allow for those patients to be searched by those secondary identifiers. But the primary identifiers are used to match the patient, so that when we get events for a patient with that identifier, we know that they all belong to the same patient. So the key here is like all those primary identifiers could be different ID types across health systems. Medical record number is the common one in a lot of EHRs, but certainly not universally accepted, and all those ID types could be different. So on a health system by health system basis, we actually configure the primary identifier ID types for each health system. The other thing that we did with data on demand is we made the decision that the health system will always be the source of truth. So we aren't going to try and reduce patient record duplication without the health system saying so. Essentially, the health system has either automated or manual processes that go through and try and recognize duplicate patients. And there are ways that those health systems fix that duplication and merge those patients, which results in yet another event from the health system. So we have said that we're not going to try and fix the duplication problem ourselves. We're going to say the health system is the source of truth. If they have patient record duplications, then their data in data on demand will also have duplication. And when we get a patient merge, we will process that merge just as the health system did within their system. So we always mirror the health system. We don't try and merge the patients ourselves. And the reason for that is you could actually get the data out of sync and get the patients out of sync and end up missing events for a particular patient if you're trying to merge those patients yourselves when they're not merged in the health system. So that brings us to our next next barrier to entry, and that's patient merge. Why is patient merge complex? Well, two patients, what are seemingly two patients in a health system, need to become one, which raises the question is, well, which one is the right patient? And the answer is both, right? Both of those patient records are results of real medical encounters. And so both of those patient records have real data for that patient that needs to be maintained even through the merge. So you can't just say, okay, well, the most recent one is the source of truth for this patient's data. You actually need to aggregate and merge the data versus overwrite it. So that's what we did. And to do that is much more complex than it may seem, because some data on a patient record, it makes sense to overwrite. Things like, if someone changes their address, it makes sense to overwrite that in their demographics. But things like an additional allergy or, two different sets of allergies for a patient, you wouldn't want to overwrite one or the other. You would actually want to merge those. And so what we did was we came up with this concept of upsert strategies. And upsert strategies actually have a much broader scope than just patient merge. They really apply to all healthcare data events that we consume in data on demand. So, and that brings us to kind of data aggregation. And I'll talk a little bit more about our upsert functions in the solution to this data aggregation problem. In healthcare data events, some events are snapshots. Think like patient ADT. Patient was admitted, patient was discharged, patient was transferred, versus some events are actually snapshots. Things like clinical documents are actually snapshots of clinical data at a point in time that are associated with a specific encounter at a specific time. So you wouldn't want to treat those as events that need aggregation. They're actually snapshots and need to be treated much differently than, say, the events related to an encounter like admit, discharge, transfer, things like that. So what we decided, again, was to leverage our upsert functions that we're using for patient merge. The idea being that any resource that we persist could have a different upsert strategy on both a resource level and a field level. Examples of some of our upsert functions that could be applied to different resources or fields are some fields you may apply an overwrite when you're aggregating events. Some you may apply a merge or an append onto the field or the resource as you get those events. And it really depends on the resource and the event itself. So all events essentially can't be treated the same, and that essentially caused some complexity that we had to solve with these upsert functions. We can also write custom upsert functions on a field level basis for fields that need to be merged or appended or aggregated in a custom way. So our solution here to both patient merge and data aggregation was essentially application level upsert logic that we could configure on both a resource and field level. All right, next thing that we had to deal with was order of processing this data and these events sometimes matters. Unfortunately, for first in, first out processing, when it sometimes matters, you generally have to consider that it always matters. And the reason I say that is you could probably do something to, in a complex way, to parallelize certain events based on the event type, but that adds a significant amount of complexity to your architecture. And I'm not sure if the complexity is worth it versus just considering the entire event stream as requiring FIFO processing. So now there's additional complexity when you do that, and that complexity is error management. What happens when you get an error for a high volume stream of events or data that needs to be processed in FIFO order? It's not simple, right? You could either start rejecting requests or events, or you could queue them up somewhere and wait until the error is fixed or until the event is fixed. And that's the solution we went with, was stream control. So we actually have the ability to pause both manually or on error, fix an event, replay the errored event, and resume processing of everything following that event. And this allows us to both maintain FIFO and not block the events coming in. So they will queue up, and obviously we'll have to wait until the error is fixed. But we don't lose any events, and we don't lose FIFO with this introduction of stream control. Okay, so that was just like a few of the complexities that we went through for integrating with a single health system. And then we decided, okay, now that we've solved kind of this problem of ingesting, processing, and storing data for integrating with a single health system, how do we scale that to tens, hundreds, potentially thousands of health systems? And that introduces a whole nother level and a whole nother magnitude of complexity. Obviously, you introduce additional burden on your layer that is doing ingestion, normalization, ingestion, transforming, and persisting. There's an additional function there that layer has to perform, and that's normalization. All of these health systems do not follow the same rules for their data that they're pushing out. So you have to normalize that data somehow, then transform it to the schema in which you want to persist it, and then persist it in a way that can segregate the data safely and securely. No health system would want their data intermixed with the data of other health systems and have some sort of risk of their data accidentally being leaked when in fact someone's trying to access another health system's data. So there's additional complexity both on the kind of ingestion and transformation and normalization side, but also on the persistence layer itself. How do you save all this data in a way that it's safe, segregated, but also can be operationalized in a way that's cost effective? So I'm going to talk about some of the friction that we encountered when scaling to new magnitudes of health systems with data on demand. The first one's normalization. There's been a lack of an opinionated standard in healthcare for a long time. There's a lot of healthcare systems could be even using the same events, the same schemas, but use different implementations. And I'll give you one example that we encountered, which really hits on a lot of different points of friction here, and that's lab results. When we started implementing lab results and saving lab results in our data on demand ecosystem, our initial implementation was that all the lab results would always be sent as essentially a snapshot of all the results in one. But the lab we were working with ended up saying, well, actually, we're going to send a few results, then a few more, then a few more, all for the same report. And that introduced some problems because we essentially had to make a decision of, okay, are we going to say that every time they make an update, they have to send the full snapshot of lab results, or are we going to aggregate results for a single diagnostic report? And after talking to some experts here at Redox who have a lot of experience integrating with labs, the response was, well, it's probably 50-50 how these labs do it. So there was no easy solution here. And we had to figure out a way to normalize these things at the edges of our platform. So, this is something that Redox has done for a while, which is configurable normalization at our platform edges. So as the data is coming in from health systems and elsewhere, we need a way to normalize to our single internal data model. And that's something that at scale becomes very, very critical. So next complexity that we found was onboarding and provisioning. We had started building data on demand in a very siloed way, where for every health system, we were going to have siloed infrastructure. And the reason for that was addressing those things I had mentioned before, which was you don't want the data to leak essentially across health systems. So we decided that, hey, the most secure way, the easiest way to guarantee that is siloed infrastructure, dedicated application containers per health system, dedicated persistent layers for each health system, dedicated endpoints. And what we found was this became very manual to onboard new health systems into our data on demand ecosystem. And not only that, the infrastructure cost looked linear as we scaled, and that just wasn't really acceptable or operational long-term. So we had a lot of long-term maintenance on operational cost. And actually, looking at it, we spent about one engineering day. So 2 engineers mirroring each other, setting up infrastructure for onboarding a new health system. So 1 engineering day worth of effort per health system to onboard, looking at the scales we're trying to achieve of hundreds to thousands of health systems. The cost of that quickly just was not palatable. So we needed to find a way that we could reduce that maintenance and operational cost, even as we scaled exponentially the number of health systems in our data on demand ecosystem. So what our solution was is we needed to share infrastructure. We had to get away from this idea of completely segregated infrastructure, but we needed to do it in a safe way. So we needed to introduce multi-tenancy and do it in a way that we could still guarantee segregated data across health systems. And then the other thing that we did was automated provisioning. So our goal was that a single person from not even from our engineering team, but from our product delivery team could hit a button and deploy the infrastructure and provision the infrastructure in order for a new health system to be onboarded to start ingesting and persisting their data. So that's how we approached onboarding and provisioning, and that's something I'm going to demo shortly. So once you do introduce multi-tenancy, that in itself introduces more complications as well. Some of those complications is every health system has varying volumes and payload sizes in their data feeds. Some of the bigger health systems send, I think we've seen, volumes as high as 30, 40 messages per second from a single health system. Others just send a few a day. The other one that I mentioned already was data segregation. You still have to be able to guarantee that this data is segregated, that a query for one health system, that there's no chance that you're going to leak data from another, or a write to one health system. You have to make sure there's no chance to, that write hits the data for a different health system. So data segregation becomes a super high concern in a multi-tenant environment. FIFO. Still hard. You still need to maintain FIFO within each tenant. So doing that in a way that's performant and doesn't cause essentially strangulation of some of the lower volume feeds or smaller payload size feeds is not a simple thing. And the last one is error management becomes even harder. The error management with one FIFO stream is hard. When you're doing it with multiple FIFO streams, it's exponentially harder because you need to be able to pause one feed into your system without impacting the rest of the feeds. So what was our solution? Sorry, there's a typo here, but essentially tenant configuration management is pivotal. So every time a new tenant is added, that tenant is assigned a UUID for their environment within the system. And that UUID is literally used for everything. As a message is ingested, that UUID is used to identify the infrastructure provisioned specifically for that tenant. And the configuration management is also for processing configuration like ID types, as I mentioned earlier. All these tenants have things that are specific to that health system. So like the ID types for patient identification differ and need to be configured on a tenant by tenant basis. So all that is done with this centralized tenant configuration management that we have. And then we adopted an event streaming architecture in order to solve a lot of these other problems. Each tenant essentially has a dedicated stream where their unique ID identifies which stream their data is processed over. And but our services at the same time are actually agnostic to our tenant streams. So we have clusters of services that can consume and process data from any of our tenant streams. And as I mentioned there in the last bullet, those clusters of services are horizontally scalable. So because they're tenant agnostic, the more tenants we have, we can just increase the size of those service clusters, and then it dynamically balances the stream processing across these clusters of services. So event streaming also allowed us to maintain FIFO within each stream, which means that we can maintain FIFO within each tenant, and allows us to control each stream in isolation from others. So we can pause a single stream while still continuing processing on all the other streams, which was pivotal. And lastly, we partitioned our data store. So in order to share infrastructure but ensure data segregation, we had to make sure that the data was separated even at the persistence layer, to the point that we had guarantees that no data could leak across tenants and health systems. All right, so I'll give a quick kind of overview of what I've talked about. So we talked about some of the complexities of just the first integration, just integrating with a single health system, solving patient identification, solving patient merging and data aggregation, as well as we jumped into scaling friction, moving beyond the initial health system integration, and scaling to 10 or even 100 health systems. And so I'm going to give a little example of just a demo of our product and how we did this, or how it works in data on demand with this kind of dynamic balancing and horizontally scalable layers of our architecture. So bear with me for a second. The way I'm going to do that is I'm actually going to first demonstrate creating a new, provisioning a new health system for ingestion in data on demand. So for those that are familiar with Redox, a lot of this will look familiar, but essentially I'm going to go and create a new destination on the Redox platform in my organization. So let's see. We're just going to create a new destination, and we're going to configure it for data on demand. We're going to consume Redox API, environment ID, oops. Okay, so as I was saying before, our goal for data on demand provisioning was to have health system data ingestion be as simple as clicking a button to provision new infrastructure for a new health system. And that's really what we achieved. So all I've done is set up a new destination on the Redox platform. And of course, actually, it looks like that worked. Not sure what the error was, but it looks like it worked. I'm going to go set up as I was talking about before, we've got our unique ID types configured for this health system for the patient identifiers that we're expecting. And we're going to go set up a subscription to start listening to healthcare data events. All right, so I've just demoed setting up a new health system in our data on demand ecosystem for ingesting new patient admin events on the Redox platform and persisting them. And I want to see how far. Okay, so it looks like we're all caught up. What I'm showing now is our dashboard that's going to show data flowing through our system. It shows here on the left, shows just an overall throughput of each layer of our architecture, our ingestion layer, our projection layer, our writing layer, and then each one of these graphs actually shows on a environment by environment basis the throughput for that environment. I did some testing earlier, so that's what you're seeing there. And what I'm going to do now is, now that I've subscribed a new environment, is send some more data through that. We use a tool called Cynthia to generate synthetic healthcare data. And all I'm going to do is take some of that synthetic healthcare data, and I'm going to send it through the Redox engine to a source that I just subscribed our new destination to. So I've just sent 10,000 events to a Redox engine source, and there are actually four healthcare system, or there are 4 data on demand environments already subscribed to that source, and we have just subscribed an additional one, so we should see a 5th show up as well. Yeah, and so what we're starting to see is data flow in to our data on demand ecosystem. We've got a number of things starting to get ingested, and we could see our new environment has actually showed up in our metrics. So what we're doing, what you're seeing right now is actually 10,000 patient admin events being sent to 5 different data on demand environments. So essentially, the way you could think about it is 5 different health systems sending 10,000 patient admin events to Redox all at once. All of that being ingested, normalized, and persisted into our data on demand ecosystem and made available for query for any of our customers that have integrations set up with those health systems. It's our 10x environment throughput is looking a little low right now, but in general we've seen throughput as high as 150 messages per second into our data on demand ecosystem across a number of health systems. So we're able to scale each layer of our architecture as needed to increase the throughput of the ingestion and the streaming as a whole. All right. So I want to kind of just wrap all this up with some conclusions here. And give me 1 second, and we'll do that. So wrapping things up, ingesting and storing healthcare data is complex. Doing it at scale is magnitudes more complex. And why is that? Well, frankly, because mirroring data across data stores in a system that you may own completely is an anti-pattern. Now, mirroring data across systems that are owned by 2 different organizations is generally an anti-pattern, regardless of industry. It's really hard to keep data in sync. So, and most of that burden falls to the organizations that are trying to mirror that data, which in this case are the creators and the innovators and the software engineers that are trying to create new software in healthcare. So what does that mean? I think it means that you really need to ask yourself the question when you're integrating, does having all the data add value to your product? Is it worth the investment? I've kind of gone through our journey here of just a few of the things we've dealt with, a bit of the complexity. And you really got to ask, is that complexity worth the investment? Or is there opportunity to maybe to relieve some of that burden while still getting the same value from your product? And so with these 2 questions, you're probably asking, so why did you build data on demand at Redox? Because it is hard, and it is complex, and it's expensive to operate and maintain, even solving problems in a way that's scalable. And the answer to that is goes back to our mission. At Redox, we really do feel that we can move the entire healthcare industry forward by identifying the points of friction that every single one of our customers or potential customers have to deal with. So what are the barriers to entry for every creator, innovator, and software engineer in healthcare that everybody has to deal with just to get their product to market? If we can solve those problems in a centralized way, in a way that everyone can take advantage of, we benefit the entire healthcare tech industry. And because of that, we benefit the patients who will benefit from the healthcare tech industry moving forward. So essentially, we want to create centralized infrastructure to remove barriers to entry into healthcare integration and to reduce scaling friction in healthcare integration. And that's why we built data on demand. So that that if it's really not adding value to someone's product, that maybe they could take a look at data on demand as an alternative to trying to go through this complex journey and maintain this complex architecture. So that's all I have. David, are we going to open it up for questions now?
Hey, Tristan. Wow, that was awesome. Great job on the live demo. I think everybody was impressed to see that. A quick one off the top. Dean asked 150 transactions per second for the fire hose or all fire hoses. And then Brandon told me in the back channel, they were actually doing 3,500 a second. But I don't know if that's for all of our connections or what. So if you want to speak on that.
Yeah, sure. So right now, the most we've seen, the highest volume we've seen from a single health system is somewhere in the range of pushing 50 to 100 messages per second to Redox, to our platform. That's not to say they couldn't push more. It could just be the data that they're actually sending us, as some healthcare systems filter the data that they actually send down to what their integration partner is privileged to access. The idea is of data on demand, and the way we've architected is we can scale to whatever necessary. So as I showed you there in Grafana, the different layers of our architecture are independently scalable. So if we saw the throughput lagging in any one of those layers, oh, so that's Brandon. All right, thanks, Brandon. So if we saw the throughput in any of those layers lagging behind, we can actually scale up those layers of our architecture independently, and the load is balanced across those services dynamically.
Cool. Well, so that was the softball. We've got some other ones that are more in depth here, and I'll try to do the questionnaires justice. So one person said, Derek actually said, seems like there are horror stories in patient merge if identity is not 100%, or is this a lower risk than I'm thinking? And then there's an add-on from Cole. He says, imagine, for instance, that the external health system has assured you that their proprietary identifiers map one-to-one to individual patients, no reuse of identifiers, but suppose the guarantee is not 100% accurate. In fact, sometimes IDs are reused. Does the Redox strategy for linking and merging patients have built-in protections against scenarios like this? Or is the platform fully exposed to the risk that the external system's guarantee may not be accurate?
That's actually a great question, and a problem we've dealt with some health systems where we have seen an identifier come in, or the same unique identifier come in for multiple patients. And what we do when we actually pause that stream, we need to go back to the health system and basically bring this up and escalate. And that's something we built in a data on demand. Again, we can pause that stream independently and raise this back with the health system so that they can address the problem.
Very cool. I wasn't aware we did that. That's awesome. Okay, another one from Lynn. They say, how should we handle health data model nuances? For example, lying, sitting, standing, BP, pulse versus blood pressure or pulse. So like different vernacular for the fields. How do you add farther qualification in a transform?
Sorry, you cut out there for that last part of that question.
Oh, sorry about that. Whoops, messed that one up. Okay, so they say how to add further qualification in a transform. So I guess mapping those two together, if they're using different
Yeah. So I'm not, again, I'm a bit of a healthcare newbie. So when it gets down to some of the nuances of the different data models, I'm not quite as strong. But what I can say in terms of normalization and transformation is you really need to make it configurable on a health system by health system basis. So and the way we solve that at Redox is we've got our normalized data model, and we've got data sets that we normalize to. And so when we get different representations for the same thing in the same field from different health systems, we'll normalize that to a single value in our data sets and our data model. I can't speak to that specific field that you're referring to, but that's how we solve the problem generally at Redox, is normalizing to the data sets in the Redox API.
Cool. Perfect. Yeah. And Lynn, if you have any more color to add, just post it in the comments, and we can come back to that. So Ken asks, this one should be good. Does Redox send a notification and then parentheses primary ID, comma new data, or actually I think that's a JSON tag in his question. So does Redox send a notification post merge?
Post merge?
I think so these questions were coming in when you were talking about merging disparate data.
Yeah.
There's others that aren't on that.
So, I mean, Redox sends a notification that mirrors the notifications the health systems are sending. So they'll send the patient merge when the patient is merged in the health system. And anything that happens post-merge for that patient will be using the merged patient ID. So there will be notifications that the patient was merged. And then after that, any notification for that patient will be using the new patient ID, which is why handling patient merge is pivotal. Yeah.
And I know we'll be talking more on that topic next week in the product webinar. So, if you can join us next week, we'll probably have some more to say there. Okay. How do we take into account alias pools / assigning authorities regarding patient identification? Sorry for all the patient ID ones here. And then the example this person uses, so how do we take into account alias pools / assigning authorities regarding patient identification? Example, 2 EMR systems providing the same type, or would they be 2 separate data feeds? This is from Nguyen.
2 EMR systems within the same health system? I'm trying to understand the scenario here.
Yeah, he's not clear. The same type. I think it's like, yeah, I guess like 2 EMRs trying to, I don't know. Nguyen, if you have more context, you could comment on that question, and we can come back to it. Sorry about that.
Yeah, you can also reach out to me in the Redox public Slack, and I'm definitely do not mind having a sync conversation or async conversation there in the Redox public Slack channel about it.
That's a great point. If you want to join our public Slack, you can join it at community.redoxengine.com and sign up, and you can talk to many different Redox engineers. I post these events there usually. So, okay, another one. How do you recover from bugs discovered internal to your processing? In this scenario, you'd have to pause, rewind, and replay, but this could leave your database in an inconsistent state, wouldn't it? And that's from Brad. And then there's another comment. How would you even detect a pause-worthy problem with respect to colliding identifiers?
So the first question. Yeah, you're absolutely right. I mean, if a bug is introduced that causes a stream to pause, or God forbid, a lot of streams to pause, we'd essentially have to do a quick rollback of whatever code change or bug happened, and hopefully we could do that quickly and then resume all feeds. Beyond that, you're right. There's when you have to enforce FIFO, you're making certain trade-off decisions, and one of those trade-off decisions is that if you've got a long outage, your database will be inconsistent for a long period of time. We've actually discussed things like sending flags on read responses to indicate, hey, this data may be out of date. We've considered rejecting read responses, but at the end of the day, we thought that it would be more useful for reads to continue on the database while we fix and resume the processing for that particular health system. So there's trade-off decisions. Unfortunately, there's no good answer to those problems, just solutions that have different trade-offs.
Good answer. I feel like you could cover a lot with that one. Okay, so there's another question about the pause. And maybe I wish I had organized these sort of around topics, so I apologize for jumping around. But pause, Dean, the first question asker asked, does this mean that you pause all customers? Does customer data overlap in your use case?
No, definitely not. And that's one of the things, and maybe I didn't spell that out or review that well enough when I talked about our multi-tenancy. All our tenants in our data on-demand ecosystem have dedicated event streams, and pausing one of those event streams will not impact the rest of them.
Cool.
So we can maintain FIFO within our event streams. We can control the different event streams on a stream-by-stream basis, and do that in a way that does not impact the event streams of our other health systems.
Cool. Okay. Yuri asks, do you auto-scale the infrastructure for every health system or use a manual process for provisioning new nodes if needed?
We don't auto-scale the infrastructure, but we auto-provision the infrastructure. So we don't use a manual process. What we can do is, again, if you remember let me find our Grafana. We invested a lot in observability in our new system, and we can actually see if any of our layers are lagging behind, and subsequently scale up that particular layer of our architecture to essentially handle the lag behind. We can scale them up and down as needed, but that is manual right now. So if we notice a part of our architecture, in this case, it looks to be our writes, are slower than the rest of our system right now. And so what we could do in order to catch up and keep up is just scale up more containers for that layer of our architecture, and the load for all the health systems would be redistributed across those containers, and hopefully increase the throughput at that layer. So that's manual, but the provisioning and the onboarding, which is what I demonstrated by creating a new destination, that's all automated. So new event streams get created, new partitions are created in our data store, and there's nothing manual needed for that processing to start beyond just turning on the subscription like you would for any destination on the Redox platform.
Cool. Okay, so there's another question about merging identities, but we've talked a bit about that, so I'm going to skip to. We have another one that's how do you deal with dependent data from different streams? I'm curious about this too. So David asks, if you're matching a current patient's name with an appointment, and he assumes that the patient and appointments are on different streams, how do you match the two?
So those will come across, if it's a patient and an appointment within the same health system, those will actually be on the same stream. And in our data store, we actually assign unique identifiers to unique resources in our data schema. So in this case, the unique resources are the patient and that patient's appointment. And that patient's appointment will actually have a reference to the unique identifier of that patient. So our data store is relational, and we match data across data models like scheduling, appointments or visits, and patient using unique references that are internal to our data store.
Okay, and then related, a fast follower, Michael asks, for a single health system that has clinical and claims data from a patient or from a payer, do you also deduplicate information across the different data sources in the data store?
Single health system that has clinical and claims data from a payer. Assuming the source of, it's a little hard for me to kind of untangle this one, but assuming the source of the data is coming from a single place, which seems like that's what you're saying for a single health system. We basically rely on our upsearch strategy. So where it makes sense to deduplicate and overwrite, we do that. Where it makes sense to aggregate or append, we do that. And that's really on a resource or field level. I'm not sure if that answered your question, Michael, but
two different sources.
Two different sources. We don't.
One EHR, one payer.
Right. So in general, what we've said at this point is that health systems are the golden source of data, and we don't necessarily mix, or we don't mix that data. So we don't allow for a payer to write to a health system's data in our data on demand ecosystem. We would consider that an anti-pattern. What we'd recommend for a scope like that is the payer write back to the health system, and then the health system send a notification that we can then process and persist into their data on demand environment.